Hello students, today we are going to discuss the beta decay process. So first we have discussed alpha decay process. Now we are moving to beta decay process. So beta decay is a radioactive decay process in which beta plus particle, beta minus particles are emitted. Basically beta plus is positrons, beta minus are electrons. So the radioactive nuclei or the processes in which radioactive nuclei are emitting, they are emitting beta plus particle or beta minus particle, they are known as beta decay processes. So the most common example, one of the common example for beta decay process is the decay of 55CS137. 55CS137. We are taking a example of beta decay process. This is a radioactive nuclei which emits beta minus particle, and it emits, this is a radioactive nuclei and it emits -1 beta 0 beta minus particle, and basically here this will be 56 here, and this will be 137. And what is the element corresponding to 56? This is Ba. This is Ba. And here this is a metastable state. This is a metastable state. So this is an example of beta minus emission. And if we observe the energy spectrum of these emitted particles, if one observe the energy spectrum of these emitted beta minus particles with the help of magnetic spectrometer, then we get this type of energy spectrum. So this type of beta particle energy spectrum is observed for the beta particles when this parent nuclei is 55CS137. Here from this energy spectrum we can observe two very important aspects. That number one aspect is the spectrum is continuous. The beta particle energy spectrum is continuous in nature. This is very unlike to alpha particle. In case of alpha particle energy spectrum, this is in case of alpha particle spectrum, we have observed that this spectrum was discrete. So beta particle spectrum is continuous in nature, while this alpha particle spectrum which we have discussed earlier, that was discrete in nature. How we have explained this discrete nature? For this discrete nature, basically we have explained that this is the nuclei, this is the parent nuclei here, and it has definite spin and parity. It has definite spin as well as parity, and when it emits the particle, by emitting the particle, basically it converts into a nuclei. It changes into the nuclei which also has definite parity as well as spin. So basically what is our idea about the energy spectrum up to this point? That when a nuclei emits the particle, then this nuclei which has the nuclei which has a definite spin and parity, this will emit the particle and it will convert into another nuclei again having definite spin and parity. This was our idea. But here in this case we are getting continuous spectrum. We are getting continuous spectrum. So on the basis of this type of thing, one cannot explain this continuous spectrum. So one cannot explain this continuous spectrum on the basis of this thing, on the basis of which we have explained the discrete nature of alpha particle spectrum. So this is one important thing which we have observed with the help of this energy spectrum for beta particle. Number 2, we have obtained here at the larger energy size, high energy side, we have obtained two peaks. We have obtained two peaks, K and L. These two peaks are corresponding to, these two peaks are obtained corresponding to internal conversion of electrons by gamma rays. So these are two important aspects which we can observe with the help of this energy spectrum. Here you can also observe one thing, that on this side, on the high energy side, there is the maximum. This point is representing the maximum energy carried by the beta particle. This is also known as endpoint energy. This is also known as, this energy is known as endpoint energy. So basically endpoint energy is the maximum energy that is carried by the beta particle. So when a sample of this nuclei, when we have a sample of this nuclei, then this sample is emitting beta particles of different energies, and this energy spectrum or the energies carried by these beta particles is continuous in nature. And these beta particles have energies, can have energies, all possible energies in between 0 and this E beta maximum. They can have all possible energies. So this type of continuous spectrum is observed in case of beta particle energy spectrum. And another important thing is the presence of two peaks corresponding to this K and L. Here we are observing these peaks are obtained due to the internal conversion of electrons by these gamma rays or by the gamma photons. So these two important aspects we can observe from this. Now there will be one another important aspect which is observed experimentally, which is not observing from this plot, but another important aspect which is observed with the help of this experiment, that suppose this nuclei is at rest, this parent nuclei is at rest, and it is emitting these two particles, beta particle and this nuclei, resultant nuclei. This beta particle is having some kinetic energy, it is moving with some kinetic energy. Here this plot is showing this. It means after the reaction, after the emission, basically this beta particle, we have we have one beta particle, this beta minus particle, and suppose this is moving in this direction with some momentum, p beta. It is moving with some momentum. Then according to conservation of linear momentum, the recoil momentum of this nuclei, recoil momentum of this daughter nuclei Ba should be equal. It should have momentum Pba, its recoil momentum Pba should be exactly equal to p beta, momentum carried by this beta particle, and this recoil momentum should be exactly in opposite direction. So after the emission, this deuter nuclei should have a recoil momentum in the opposite direction of beta particle. Whatever momentum beta has, then the momentum of this recoil nuclei should be in opposite direction, and this should be equal. But experimentally this thing is not observed. But experimentally this fact is not observed. This fact is not observed. It means this process doesn't follow conservation of linear momentum principle. Conservation of linear momentum principle. So this is another fact which is observed experimentally. Their momentum should be exactly in opposite direction, but experimentally this is not observed. Apart from this, another important aspect that is observed about this. So fourth point is, which is observed experimentally or even theoretically, you can observe this, that the ground state of this CS nuclei, I can remove this. So ground state of this is suppose Ji, this is Ji, then this is equal to 7 by 2 H cross. This is 7 by 2 H cross. So ground state spin of 55 CS 137 nuclei is 7 by 2 H cross, while this metastable state of 56 BA 137, it has spin 11 by 2. It has spin 11 by 2 H cross. And this beta minus particle, which is electron, it is carrying half H cross. This is the spin. Spin of this beta minus particle is half H cross. Now, by combining this 11 by 2, and this half spin, we can never get this 7 by 2 H cross or this 7 by 2. They cannot be equal. On this side, we will have integer. Resultant will be some integer. And here, on this side, basically we have half integer spin. So, on the basis of this, one can say that the angular momentum is not conserved. Angular momentum is also not conserved. So, one can say that in this process, angular momentum is also not conserved. This is the fourth point. So basically these four different type of aspects are observed in beta decay. So this was a challenge to explain these 4 different aspects which are associated with the beta decay process. To understand these 4 basic facts about this beta decay process, there was a scientist whose name was Pauli. So Pauli produced his hypothesis. So Pauli produced or postulated Pauli's neutrino hypothesis. Neutrino hypothesis. So to explain these 4 facts which we have discussed, basically Pauli produced neutrino's hypothesis. In this hypothesis, he postulated a new particle. To whom he was saying that this is neutrino. It was represented by nu. This was represented by nu. And according to Pauli, this neutrino particle is also emitted in this beta decay process. So what he was saying, that this new particle which is known as neutrino, this is also emitted in this beta decay process. So in the beta decay process with beta particle, a neutrino particle is also emitted, and this neutrino carries the rest energy. Maximum energy emitted by or carried by the beta particle is E beta max. This is the maximum energy that is carried by the beta particle. And suppose this is the maximum energy that is carried by beta particle, and if suppose we have another beta particle which is carrying energy k beta, then the difference in this energy or the rest energy which is not carried by this beta particle, that will be E beta maximum minus k beta, and this energy will be carried by this neutrino. So what he was saying, he was suggesting that in the beta decay process another particle, neutrino, is also emitted, and this neutrino carries the extra energy that is not carried by the beta particle. Suppose one beta particle is carrying energy k beta, but maximum kinetic energy that can be carried by beta particle is this one. So where is the rest amount of energy? Where is this? This is carried by this particle neutrino. So in this way, conservation of energy principle is followed. So by this hypothesis, and by saying that this neutrino is emitted in this process along with beta particle, he was satisfying, or this hypothesis was satisfying the conservation of energy principle. So with the help of this neutrino particle, he explained the conservation of energy principle. So in this way, he was able to satisfy the conservation of energy principle. If this particle is emitted along with this beta particle, then what other properties this neutrino must have? Properties. If you observe this equation, then charge is satisfied throughout the equation. In this equation, charge is satisfied. Charge is already conserved, so it must have zero charge. So property of this neutrino is that it must have zero charge. Zero charge. Why we are saying that zero charge? Because charge is already conserved. Charge is already conserved. Second aspect is its mass. Basically, its mass must be zero or it must be almost zero. Mass of the neutrino. Second is mass of the neutrino. Mass of the neutrino must be zero. Must be zero or almost zero. Almost zero. This is another property. This is another property. Third is its spin. Third is its angular momentum spin. Angular momentum spin. Angular momentum spin. Momentum spin of neutrino must be 1/2 h cross. 1/2 h cross. So it must have a spin half. This must be a spin half particle. So because if this is carrying half spin, then on this side this is carrying 11/2 spin. Its spin is 11/2 plus this beta particle, this is carrying half spin, and suppose neutrino is also emitted, then it will also have half spin. Now spin of this is 7/2. Spin of this is 7/2. If we combine these three, then we can achieve, by the combination of these three, one can achieve this 7/2. From this, one can achieve this 7/2 spin. Or you can say in another word, whatever spin will be here and whatever spin will be here, the difference in these two J values, so whatever spin we are getting on this and whatever spin we are getting on this, the difference in between these two J values or two spin should be integer, will be integer. So in this way basically angular momentum will be conserved. So how angular momentum is conserved? For the conservation of angular momentum, the difference between the J value on both sides should be integer. It should be integer. And if you combine 11/2, this 1/2 and this 1/2, then we will get some half integer value, and difference between these two will be some integer. So due to this half spin carried by this neutrino, basically angular momentum will also be conserved. This angular momentum will also be conserved. Apart from this, when this particle is there, apart from this presence of this neutrino will also satisfy the linear momentum. So conservation of linear momentum will also be satisfied. Why? Will also be satisfied in the presence of this neutrino, because now there will be three particles. Now here there will be a momentum associated with this, there will be a momentum associated with neutrino, and there will be some recoil momentum. So there will be three momentums, and combination of these three or resultant of these three momentum should be zero. Resultant of these three momentum will be zero. So now it's not necessary that the recoil momentum of this Ba nuclei will be just opposite to this. So this condition is not there now, and it is due to the presence of neutrino. So in this way, the presence of neutrino also satisfy the conservation of linear momentum principle. So conservation of linear momentum principle may also be satisfied in the presence of this neutrino particle. So these are the properties of the neutrino. Apart from this, there is one important fact about neutrino. Apart from these properties, there is one more important fact about these neutrino, and that is there is an antiparticle of this. We have neutrino, and this neutrino has an antiparticle. And this antiparticle is known as antineutrino. This is known as antineutrino. This is represented by nu bar. This is represented by nu. This antineutrino has most of the properties similar to the neutrino. Mass is almost zero. Mass of this antineutrino is almost zero. Spin of this antineutrino, basically mass is zero, charge carried by this is zero, charge carried by this antineutrino, that is also zero, and its spin is also half. Its spin is half h cross. But where is the difference between these two? The difference is this neutrino is left-handed particle. What is the difference? This neutrino is left-handed particle. While this antineutrino, this is right-handed particle. This is right-handed particle. This is left-handed particle and this is right-handed particle. So for this, if this is spinning like this, then this will be its spin. This will be the direction of the spin. This will be the s of this nu. While in this case it will spin like this, and this will be the direction of this spin. This will be the spin of this antineutrino. So this is left-handed particle, this is right-handed particle, and because this is left-handed particle, so basically its spin will be opposite to its momentum. So the momentum that is carried by this, that will be in opposite direction. This will be the direction of nu. While in this case, momentum will be in the same direction. While in case of this antineutrino, basically spin as well as momentum, they will be parallel, while in case of neutrino, spin and the momentum, they will be antiparallel. So these neutrinos are left-handed particles, and these antineutrinos, they are right-handed particles. So this is the difference between them. So basically on the basis of these particles, neutrino and antineutrino, Pauli has explained all the 4 problems which we have faced in explaining this continuous spectra exhibited by the beta particles. So now, by including this particle here, this is electron, this beta minus emitted with this beta minus particle, and this will be associated. When this particle will be emitted, there will be an associated emission of this antineutrino. There will be an associated emission of antineutrino. Now this equation will be complete. In this way, basically on the basis of his hypothesis, Pauli was able to explain most of the points which are raised in the energy spectrum or beta particle energy spectrum of beta decay process. Later on, Fermi gave his theory of beta decay, which was based on quantum mechanics, and on the basis of his theory he was able to explain this continuous behavior of this beta particle energy spectrum, as well as he was able to find out the decay constant lambda. So next is Fermi theory of beta decay. Fermi's theory of beta decay. Fermi's theory of beta decay. Beta decay. His theory was also based on Pauli's neutrino hypothesis. So his theory was based on Pauli's neutrino hypothesis. Basically, he used quantum mechanics to find out the continuous spectrum and decay constant. So with the help of this, in this theory, he used quantum mechanics. And on the basis of this theory, he was able to explain the continuous behavior of beta particle spectrum. Second aspect what he has calculated was decay constant. He was able to find out the decay constant. So he was able to find out these. After this, basically he has also find out the Fermi-Curie plot. He was also able to draw the Fermi-Curie plot. And in last, he find out FT parameter. To compare the decay probabilities of two nuclei. So FT parameter to compare decay probabilities of two nuclei. So on the basis of his theory, he was very successful, and basically he find out all these aspects on the basis of his theory. Fermi derived an expression of decay constant lambda from the initial state of the parent nuclei to the final state of the daughter nuclei. So basically there will be an initial state of the nuclei, and suppose initial state is represented by psi I. This is the system, this is the initial system, this is the wave function of the initial system, and by beta decay it will change to another system, and suppose that system is represented by psi f. So basically for this process he find out the lambda. he find out the lambda. So he find out lambda from the initial state of the parent nucleus to the final state of the daughter nucleus. The transition probability in his theory, the transition probability per unit time lambda from initial state psi I to final state psi f is given by time dependent perturbation theory. So basically this lambda, whatever lambda he was trying to find out, he find out this lambda on the basis of time dependent perturbation theory. And on the basis of this time dependent perturbation theory, he find out the relationship lambda is equal to 2 pi by h cross. This is 2 pi by h cross HIF square dN by DEF. So basically, to find out lambda from this initial state of the nuclei to the final state, basically he used time dependent perturbation theory, and he used this formula. Of lambda. This formula is also known as Fermi-Golden rule in quantum mechanics. You are aware about this by the name of Fermi-Golden rule in quantum mechanics. Now first question arises, what is this HIF? Basically this HIF is equal to psi f, h and psi I. Now what is this? This is the Hamiltonian. This HIF represents the Hamiltonian, or this represents the Hamiltonian of interaction between initial and final state. So this HIF represents the Hamiltonian of initial and final state, Hamiltonian of interaction between initial and final state. If you calculate the HIF square, then square of the modulus of HIF, if you calculate this comes out to be G square. This will be MIF square. This is G square MIF square psi beta square, and this psi nu square, where this G square represents the coupling constant for weak interaction. This G basically not G square, this is coupling constant for weak interaction. Coupling constant for weak interaction, its value is nearly 10 to the power minus 49, and this is gram centimeter to the power 5. This will be centimeter to the power 5 and second minus 2. So this is the value of this coupling constant for weak interaction. What is this MIF? MIF is the square modulus of matrix element of interaction between initial and final state of the nuclei. So this is square modulus of matrix element of interaction. So this represents the matrix element of the interaction between initial and final state. This psi beta is the wave function associated with beta particle. Associated with beta particle, or you can say beta and this neutrino, with beta and neutrino. So this is interaction Hamiltonian. This HIF is the interaction Hamiltonian. Interaction between what? Interaction between the perturbed initial state of the nuclei. Interaction between the perturbed initial state of nuclei with large number of final states. With large number of final states. Because the perturbed initial state is interacting with the large number of final states. That's why we are getting continuous spectrum. And this represents dN by dEF. This represents the density of this large number of final states. This represents the density of large number of final state. So basically he find out decay probability. You can say on the basis of this, you can say that he find out this decay probability on the basis of overlapping of the state of perturbed parent nucleus. Overlapping of this psi I wave function, perturbed wave function of the parent nuclei with large number of states available in the final state. He obtained an expression. On the basis of this, he obtained an expression for the probability of emission of beta particle. So on the basis of this, what he has find out, what type of expression he derived? He derived an expression for the probability of the emission of beta particle per unit time within the momentum interval PE and PE d plus dPe. So basically in the momentum interval, he find out the probability of emission of a beta particle per unit time. So PE, what he has calculated, he calculated this PE dPe. This is the probability of the emission of beta particles in the momentum range, which are carrying momentum range in between PE and PE plus dPe. PE, and these particles are suppose carrying energy E beta out of the total energy E beta maximum. Then this will be equal to, this will be, you can say, proportional to, this probability will be proportional to E beta maximum minus this K beta and square of this. This will also be proportional to P square dPe. So he obtained this type of expression. If you write down this expression completely, then final expression will be like this. We will get this type of final expression. This will be P dPe will be equal to, dPe is equal to m square. This will be m square. This will be g square. Sorry, this will be g square. Basically, this is the coupling constant. Matrix element MIF of interaction. Matrix. This will be MIF square divided by 2 pi cube c cube. This will be 2 pi cube c cube. And this will be h cross to the power 7. And here it will be E beta maximum minus minus. This will be energy carried by beta particle. This will be square of this, and this will be PE square and DPE. They find out this expression. But when they plotted this PE, as a function of this K beta, when they plotted this PE as a function of K beta, they find out same type of energy distribution, beta energy distribution spectrum for the emission of beta plus particle as well as for beta minus particle. So when they plotted this PE as a function of this K beta, what they find out? They find out the continuous spectrum of beta particles for beta plus and beta minus emission for both particles, but shape of both these particles will be same. Beta plus particle spectrum shape was exactly similar to beta minus particle spectrum shape, but experimentally their energy spectrum shape was different. So they were missing. He was missing. Basically, Fermi was missing something here. So what was the missing aspect? Missing aspect was the Coulombian interaction. So when a nuclei is emitting a beta particle, then behind this there will be another nuclei, and this emitted beta particle, either this is beta plus or this beta minus, this will interact through Coulomb interaction. It will interact with this deuter nuclei through Coulomb interaction. So he was missing this Coulombian interaction. So this deuter nuclei, it will carry positive charge. Now if beta plus is emitted, then repulsion interaction will be there, and if beta minus particle is emitted, then attractive interaction will be there. So basically in both cases different type of interaction is playing. That type of thing was missing here. Up to this point he was considering beta emission and beta plus emission and beta minus emission in a similar way. That's why he was getting same type of energy spectrum. But to include this aspect, Coulombian interaction aspect, into this theory, he included a correction factor. And this is denoted by F ZD. This is the Z number for deuter nuclei, and K beta. This is a function of K beta and ZD. So he included this factor. This is the correction factor, which is also known as Fermi factor. This is known as Fermi factor. And actually, this is a correction factor. This Fermi factor is a correction factor for Coulombian interaction. Coulombian interaction between beta particle and deuter nuclei. And expression for this correction factor was, this was F, this is ZD, K beta. This was equal to 2 pi eta divided by 1 minus e to the power minus 2 pi eta, where eta is equal to plus minus ZDE square upon 4 pi epsilon naught. This will be H cross V, where this V is the velocity of the beta particle. This V is the velocity of beta particle, beta plus particle or beta minus particle. ZD is the charge number of the deuter nuclei. And this plus sign here, what is important here? This plus and minus sign is important. This plus sign is for beta minus emission. is for beta minus emission, and this negative sign is for beta plus emission. So basically this factor will be different for beta plus emission and beta minus emission, and this factor is, correction factor is included to compensate the Coulombian interaction that is taking place, the beta particle and the deuter nuclei Now on the basis of this expression, when they plotted a graph between this decay probability, so basically what they had done, after obtaining this expression, they plotted a graph between this PPE. They plotted a graph between PPE as a function of this K beta. They plotted two graphs. One for beta minus emission, and another for beta plus emission, and second graph for beta plus emission, and second graph is for beta plus emission. Here again they have plotted between PPE versus K beta, and they find out two different shapes. For beta minus emission, they find out this type of shape. Which was matching with experimental results. And for beta plus, they have obtained this type of shape. And both these shapes were matching more or less with experimental results. Their shapes was matching with experimental results. So on the basis of these plots, basically they find out the exact continuous shape of the beta plus and beta minus emission energy spectrum. So they have plotted here they have plotted the probability of emission of beta particle, this PE, probability of emission of beta particle as a function of the energy carried by the beta particle. So on the basis of the graph, they find out exactly same continuous shape of these plots what is obtained experimentally. After this, what they have done, they have also plotted one more graph. From here, so I am removing these two graphs. From this expression, they have obtained one more graph, and that graph was in between. This PE, square root of this PE. So they have plotted this graph, this PPE divided by this PE square, and this factor, this PE square and this correction factor F ZD, K beta, and square root of this. One can observe that if we take this type of term, PE is here, and take this PE square and this F factor here in denominator, then this will become proportional. Square root of this will become proportional to E beta maximum minus K beta. So if we plot a graph between this quantity and this K beta, then we are going to find out a straight line. Like this. So plot this graph. Here this will be K beta, this will be K beta, and here this will be, I'm writing it like this, this is K beta, this is E beta maximum, this will be E beta maximum minus K beta. And here I am again writing this factor, this PPE upon PE square, and this is F ZD K beta. So if you plot this, if you plot this function as a function of this K beta, and according to this proportionality you are going to find a straight line, and this straight line will be like this. You will find out this type of a straight line, this straight line, and here this point will be corresponding to K beta maximum. This is known as end point energy. This is for end point energy. We have plotted this graph by assuming that mass of this neutrino particle is exactly 0, and this type of plot exactly matches for the plots for allowed transition. This type of plot matches with this plot matches with this plot matches with allowed transition plots, allowed transitions plot. Basically in beta transitions, basically there are two types of transition. One transition is known as allowed transition, another is known as forbidden transition. We will discuss these things later on, but here this type of plot was exactly matching for allowed transitions, and this plot is known as Fermi-Curie plot. This is known as Fermi-Curie plot. However, here there is one thing: if exact mass of nu is taken, then there will be a little bit deviation. There will be a little bit deviation from this. If you consider the exact mass of neutrino, if m nu is not equal to 0, if m nu naught is not equal to 0, then there will be a little bit deviation from the straight line, and here this will be equal to this endpoint energy. It will become K beta maximum minus m nu, rest mass energy of this neutrino. This will be. However, if we observe this type of plot for forbidden transitions, then in general they are not straight line plots, they deviates from the straight line behavior. However, you can write, so basically for allowed transition, this type of plots are matches with the experimental results, but for forbidden transitions, this type of plot, deviates from a straight line, So for allowed region, plot between these two quantities will be nearly straight line, while for forbidden transition it deviates from the straight line. So whatever plot they have find out, that was exactly matching with allowed transitions. Apart from this, they also find out a FT parameter. FT parameter or comparative half-lives, and with the help of this FT parameter or comparative half-lives, one can compare the beta decay probabilities in different nuclei. So on the basis of this, one can also find out the FT parameter. So this expression is quite good in explaining lot of things. So comparative half-lives. So next is comparative. On the basis of this, you can have comparative half-lives. These FT parameters are used. These FT parameters are used to compare beta decay probabilities of different nuclei. So how we will calculate this FT parameter? We will again use this one. So decay constant lambda, you are aware from radioactivity that decay constant lambda will be equal to how much? 0.693 upon T half. From this, how can we calculate this lambda? This will be integration of this PE into dPe. From where? From 0 to maximum value of PE maximum. This is PE maximum. So integrate this. On integrating this, what you are going to find out on this side, this will be G square divided by, this will be 2 pi cube C cube H cross to the power 7. This will be M matrix element of interaction will be square integration 0 to PE maximum. I am writing this correction factor first. So this will be F ZD K beta, and here this will be this E beta maximum divided minus K beta square of this. This will be PE square. This will be PE square into dPe. Now we will make this integration dimensionless. This term is already dimensionless, this correction factor. And if we divide this square, this is energy square. So if we divide this by me square C to the power 4, then this will become dimensionless. Similarly here, divide this by me square C square and this by me CE. So in this way, all these terms will become dimensionless. So we have divided this by me to the power 5 C to the power 7. So here in denominator we have multiplied by me to the power 5 and C to the power 7. So we will multiply this same factor by the same factor, me to the power 5 and C to the power 7 here. So we have multiplied numerator as well as denominator by this factor. Now what will happen? This will become dimensionless, and this is known as, this dimensionless integration, this is known as F value. So how this F value is defined? This F will become a function of this ZD. After integration, this will be a function of ZD and this E beta maximum. So this will be a function of ZD and E beta maximum, and its value will be integration 0 to PE max FD FZD E, this will be K beta, this will be K beta FZD K beta, and here it will be E beta maximum minus K beta square divided by ME square C to the power 4. This will be PE square upon ME square C square, and this will be DPE by MEC. So if we replace this integral by this factor here in this equation, then this equation will become, so we will multiply this T1/2 with this factor and we will write here. So this equation will become FZD E beta maximum multiplied by T1/2. So this will be FT value. This will be the FT value which can be used to compare the beta decay probabilities of different nuclei, and this will become equal to, take this 0.693 here, this will be 0.693. This C cube will be cancelled out and here we will left with C to the power 4. So here this will be 2 pi cube H cross to the power 7, and here it will be G square ME to the power 5, this will be C to the power 4, and here it will become Mij to the power -2. So now this is the expression of FT value, and by comparing this value for different nuclei, we can predict that which nuclei has higher probability for beta decay. These FT values varies from 10 to the power 3. These FT values vary from 10 to the power 3 to 10 to the power 22nd. From 10 to the power 3 second to 10 to the power 22nd. So on the basis of this FT parameter, we will basically compare different nuclei for their beta decay probabilities.